Hello everyone, my name is Evangelos Spyrou and I'm coming from the Hellenic Institute of Transport from the Center of Research and Technology Hellas, and we will be talking about the subject of discrete concavity of packet reception ratio utility functions. Okay, I seem to have the same problem, let's see. Yeah, okay. So a brief overview, we will briefly describe the problem, then we will give our approach, some insights on the theory. Then we will be creating the PRR function into a concave up one. We will give the implementation and numerical results and some conclusions to finish with. The problem is basically that the wireless stack consists of multiple layers. It's the application layer, the network layer, the MAC layer, and the physical layer. Okay, what we're working on in this work is on the network layer. And in order to be able to analyze theoretically network layer parameters, we have a major complexity into actually working with them, as we will see later on in this presentation. One of the significant parameters that exist in the network layer is the packet reception ratio. Note that the packet reception ratio can be counted as the packets that have been received divided by the packets that have been sent. So you can see a paradox here. You can see a very simple way of actually calculating the packet reception ratio and a very complex theoretical work that exists in its calculation, as we will see later on. The PRR optimization, the packet reception ratio optimization, can reduce the interference and the collisions of the transmission by using the transmission power. You can imagine that if I extend my transmission power, then I'm actually increasing the interference of other nodes around me, and I can create more collisions. The solution is the employment of the packet reception ratio as a concave function, as a concave up function, because we actually diminish the complexity of the theoretical model. So basically, we analyze the PRR formula using some networking terms in order to transform the PRR function to concave up. So in order to be more specific, what we do is that we do an analysis on the time domain, not on the frequency domain. We inform that each node of the network can be duty cycled in order to ensure that message collisions are measured. Duty cycling, what do I mean by duty cycle? Duty cycle means that I'm a node and I sleep, my radio sleeps, then I wake up, I transmit, I sleep again. That's called duty cycle. I'm just waking up to transmit my data, and that's all. Okay, so we consider that the duty cycle mechanism will take into account the hidden terminals of its transmission. The hidden terminal is when we have two sets of nodes and one of them is within the range of the other without it knowing its presence. So as you can imagine, if we both transmit, then since one of the nodes is within the range of the transmitting nodes, then we will have a packet drop without knowing the presence. If we know the presence of the node, it's called an exposed terminal. So basically, with our approach, the interference is mitigated and collisions are eliminated. And because we will make this into a concave up function, then we can utilize efficient algorithms to solve our problem. The theory behind it is that concave functions constitute problems that pose tractable optimization to the local optimum, which is the global optimum. For a function f, it is concave if the first equation that we can see on this slide is being satisfied, and a discrete concave function for the univariate case is the one that satisfies the equation f to x minus 1 plus x to f to to x plus 1 is less than equal to 2f of x. And for the discrete concave up function is the opposite is greater than the 2f of x. As we said previously in this presentation, we will actually investigate the theoretical model of the packet reception ratio. As we can see, it can be expressed by approximation as a function of the bit error rate, which is represented by xi here, or xi for the Greek native speakers. Okay, so the L is the packet length in bits, and the bit error rate is given by the formula which has on its exponent gamma, which gamma is the signal to interference and noise ratio, and it's given by gamma I of j equals hi of comma j p I divided by the summation of the interference p t h t j plus the noise, the white noise. Okay, so you can imagine that if we want to optimize the transmission power of the sending node, which is PI, and use this as a strategy, for example, in an optimization problem, then we do have a very complex environment. So what we need to do is that we need to show that it's the utility function of the summation of the PRR ij is either concave down or concave up, depending on what we want to do. And we know that, for example, by concave up, we mean convex. Okay, it's convex and concave. So basically, we consider the following utility function, which is CIPI, which is concave term, minus the summation of j to n of PRR ij. And we need to make sure that the second term, which is the summation of j of n of PRR ij, is concave down, because the negative will be concave up. Altogether, we need to show that what you can say in the middle of the slide, that the summation of the PRR ij to, let's say, x of x minus the summation of PRR ij, the first strategy, minus the PRR ij of the third strategy is greater than equal than 2 times the C1 CIPI of the second strategy minus CIPI of the first strategy or value, if you want, if you like, minus the CIPI of the third value. So what we do is the following: how we implement it in the time domain. As you can see in the figures below, if a sender transmits at the same time slot with with another sender, then we will have a message collision, and one of the messages will be dropped. So what we do is that we actually duty cycle the nodes in order to. It's a very simple mechanism. We duty cycle the nodes to transmit in different slots. So we exchange a bit the slot. Okay. So this is what we actually do. And we proceed with two propositions for the general case, and when CI, which means that the price, the cost is 1. The proposition states, the first proposition states that if there is a duty cycling, the nodes of the neighborhood and the interference are presented, then the utility function that you can see in this equation in the middle of the slide is concave up. If there's interference at the denominator of the signal to interference and noise formula, then we keep the same value by duty cycling, and then the utility function of the PRR will keep the same value as well. So what we do in simple words is that we duty cycle the nodes so that we either by using a different transmission power we keep the interference at the same level, and we actually have the same sign. Hence, the condition of concavity will be satisfied. The proposition 2 states that when CI is 1, the utility function starts by being concave down and moves by being concave up as the increase of SINR. That's something that we cannot avoid because we do not have concave concave price or cost, if you like. Uh, Now, for the implementation, our network has a total or 4 nodes for simplicity because we need to show the efficiency of our approach. We assume that the neighborhood of the node has 4 nodes as well, and we normalize the values of the utility function in the range 0 to 1, just because we cannot have, like, let's say, for example, 800 microwatts and then have the packet reception ratio which is below, which is between 0 and 1. Then we will have a bias. For example, we will have something that will essentially won't work. And we ensure that neither two terms has a greater weight than the other. That's what we assume. The numerical results, as we can see in figure 3, the utility function is concave up, allowing a global solution when interference is at a low level and very small transmission powers are not used. Here, what we see is the following, as we will see in the following slide. The packet reception ratio, usually, when we use small transmission power levels, fall into the percentage of less than 20%. Because of the low signal quality and so on. So we don't want to do that. The interference, even with minor interference, our packets are dropped. So we actually cut that from our solution in order to be able to make our solution our function concave up. Now you will see what I mean in the next slide. Uh, First of all, when we have no interference, the utility function is linear as we see in the figure 4. Now, check what happens if there's small interference. In, in this in figure 5, we can see that we have a peak in the beginning. So, in order to be able to make this into a concave function, we actually diminish the the small transmission power levels because we don't need them, and we play in our gray area. What do I mean by gray area? The packet reception ratio being between 20 and 90%. So what we do is perform our optimization in this area so that we can have better results. And the result is given here, as you can see. Now, as a conclusion, we investigated a function which is a wireless network layer function describing communication reliability in the form of the PRR. We actually make it easier to solve by using duty cycling terms of the nodes in order to give researchers the means to actually have a simpler way of solving such a difficult problem. And our future work is to put our results in the utility function that comprises the ETX metric. The ETX is the expected transmission count, which is 1 divided by PRR forward times PRR backwards. It's a very important metric in wireless networks. And also some of the future work that is not really present in this slide is the fact that we can use this result to game theoretic models where we actually need to show sure concavity and larger midpoint property satisfaction in order to be able to analyze the equilibriums that are going to be found. And one final slide. Our study investigated the function, which is a wireless network layer function, describes communication reliability in the forms of the packet reception ratio. Then by using duty cycle terms of the nodes, our study makes an easier solution to create the function concave up. Our solution provides researchers of a tool to optimize network layer parameters and essentially to assist discrete optimization using game theory. And as I said previously, and our results can be utilized in discrete game theoretic models in the network layer of the wireless stack, something that we're aiming to do for a journal publication. We aim to show a tutorial where you actually get something out of this work in order to actually formulate a problem and solve it efficiently in the discrete space. Uh, Thank you very much for your time.